Is the last today a longer one?
I'm not 100% sure. I don't think it's very long. This will actually be the first time I've taught it. Um, so, homework number 9 on chapter 10 and 11 is due on the 3rd. The exam on chapters 10, 11, and 13 will be on the 10th. On the 8th, we'll have a day of review. It's going to be 10 questions. I've got it more or less worked out. So if you do need to take it early because you have to leave early or something, just meet up with me and we can work out a time to do it. Last lab will be today. I don't think it's super long, but where did I put it? I did not put it in this spot. But so I think this should be straightforward. I think it'll be a lot like the other pulley lab, but now we're using the multiple pulley. So we're talking about oscillations, about equilibrium. We've skipped from chapter 11 to chapter 13. We will have a little time at the end. So I'll cover some of chapter 12 at the end, but it will not be on the exam. The exam is chapters 10, 11, and 13. So oscillations about equilibrium. So if you have like a mass on a spring and you set it in motion, it will oscillate. So we're going to start by talking about what periodic motion is. Then we'll talk about simple harmonic motion. We'll talk about the connections between uniform circular motion and simple harmonic motion. We'll talk about how we can calculate the period of we'll work out the period for the like classic example of a simple harmonic motion, which is a mass on a spring. Then we'll do energy conservation in oscillatory motion. The pendulum, damped oscillations, and driven oscillations in resonance. So period is the time required. So periodic motion is any sort of motion that repeats, like, a weight on a pendulum. It repeats over and over again. And the period is the time required for one full cycle, the time for it to get back to where it started, to repeat. So period is usually written with a capital T because it's a time. Frequency is 1 over the period. So frequency is 1 over period. The unit is inverse seconds. This is also called hertz. So you may have seen various things labeled with frequencies in hertz, like radio stations are in kilohertz or megahertz. Your cell phone might be in gigahertz, or this, this is using 2.4 gigahertz to transmit to the computer. Those are frequencies for light. Hertz is 1 cycle per second. You may have also heard it for sound. So humans can hear sounds between about 20 hertz and 20 kilohertz. So the processing speed of a computer refers to the number of binary operations it can perform in 1 second. So it's really a frequency. And if the processor of a certain computer operates at 3.7 gigahertz, this is the clock speed of a computer. How much time is required for 1 processing cycle? So remember, period, if its frequency is 1 over period, period will be 1 over frequency. And this is in gigahertz. Remember that giga for SI for metric prefixes, giga means 10 to the 9. So our frequency is 3.7 gigahertz. We want to find the period. Well, frequency is 1 over period. So period is 1 over frequency. 1 over 3.7 gigahertz will be 1 over 3.7 times 10 to the 9 hertz, which will be 2.7 times 10 to the minus 10 seconds. That's how long one computer cycle on one processor cycle on a 3.7 gigahertz computer takes. And that's just like the clock speed. And if you overclock a computer, you're increasing that frequency. So one of the things we know is that a spring exerts a restoring force that's proportional to the displacement from equilibrium. So for a spring, force equals minus kx. Now, a mass on a spring will have a displacement as a function of time that's a sine or cosine curve. That's because, force equals mass times acceleration. So mass times acceleration equals minus kx. So you can think of this as mass times x double dot equals minus kx. This is a differential equation of second order. Second order differential equations, the solution is sine or cosine. At least one of this form. Robinson, right? So if you solve an equation like this, you'll get something like x is going to be some quantity times, say, cosine well, it would end up being square root k over n to t. So you'll have some oscillation of some amplitude A. Dante? And you'll be moving at a speed v. Speed v is a strip. V would be the speed of the strip. So here A is the amplitude of the motion. And it moves upward at some velocity. The strip of paper moves upward at some velocity v. And it would draw a cosine curve. So for a harmonic oscillator, position is a function of time. Is some amplitude times the cosine times what we'll call it omega t plus some phase phi. So if we call the period of motion t, you could write this as 2 pi over period, the time to make one cycle. And that's so we write the position as a function of time. It is a, some amplitude, times the cosine of 2 pi over the period times t. And then with that formula, it's easy to show that if you at time t plus period is the same as the position at time t, which is what you would expect. More generally written as something like this, where it's a times cosine. That 2 pi over t is called omega t plus some phase. That's the more general solution. So an air track cart attached to a spring completes one oscillation every 2.4 seconds. So remember that, we're using for x, we had, a times cosine of 2 pi period times t. That's the more general form. Completes an oscillation every 2.4 seconds. The cart is released from rest at a distance of 0.1 meters from its equilibrium position. So it starts at maximum A, that gives it a cosine curve. So the phase would be 0. And what is the position of the cart at 0.3 seconds, 0.6 seconds, 2.7 seconds, and 3 seconds. So this, we have a cart on a spring. It's oscillating back and forth. We know it makes one complete oscillation every 2.4 seconds. So that's the period. And that means x is a function of t. Is going to be the amplitude, which is given, cosine 2 pi over the period times the time. And because this starts at maximum amplitude, 0.1 meters from its equilibrium position, it will just be cosine. You don't have to worry about a phase. So if we go through and list what we know, we know our amplitude is 0.1 meters. We know our period is 2.4 seconds. And we're trying to find x at 0.3 seconds, 0.6 seconds, 2.7 seconds, and 3 seconds, respectively. So I'll let you guys work on that for a couple of minutes. So this x equals a times cosine of 2 pi over period times time. The X is going to be 0.1 meters times the cosine of 2 pi over 2.4 seconds times time. So here, for part A, 0.3 seconds, we have 0.1 meters times cosine of 2 pi over 2.4 seconds times 0.3 seconds is 0.1 meters times cosine of pi over 4, which is 0.071 meters. At 0.6 seconds, we end up with 0.1 meters times cosine of pi over 2 meters, which is 0 meters. At 2.7 seconds, we get 0.1 times 9 pi over 4, 0.1 times cosine of 9 pi over 4, which is again 0.071 meters. And at 3 seconds, we get 0.1 times cosine of 5 pi over 2, which is again 0 meters. Just a sec. And as you can see, when we go a time period of 2.4 seconds later, so 0.3 plus 2.4 is 2.7, we get the same output. And 0.6 plus 2.4 is 3, also 0. So you'll get a sine curve. The general form is something like this. And it turns out the reason this looks, we're using omega, which you might be reminded of from our previous stuff, is that an object in simple harmonic motion has the same motion as one component, just the x or the y component of an object in circular motion. So there's a connection between circular motion and simple harmonic motion. And because of that, we can define omega. So the period, and so omega is 2 pi over period, or it's also 2 pi times frequency. So if t is the period of motion, omega is 2 pi divided by the period. Or if you know the frequency, it's 2 pi times the frequency. And that's known as the angular speed, or sometimes the angular frequency. So the position as a function of time is a times cosine omega t. There is this phase term that should be technically there, just so you can start anywhere in the cycle. Generally, these are going to be nice, and phase is going to be something like 0 or, yeah. So the angular frequency, omega, is 2 pi times the frequency, or 2 pi over the period. And the unit is just still inverse seconds. Now, one of the nice things is that, well, now we have a function. We can take a derivative. We have a function of x in terms of time. If we want velocity, well, that's just the derivative. So velocity as a function of time is just a omega cosine, oops, not that. Velocity is minus a omega sine omega t plus phase. And then acceleration is minus a omega cosine omega t plus phase. And here we have our equation. We can see that this, mass times acceleration equals minus kx. So acceleration is minus k over m times x. That should be squared. And so we can see that omega, and for a mass on a spring, is omega squared is equal to k over m. So omega is square root of 2. So both of these can be found by taking components of the circular motion quantities. We're just taking the derivative. So, derivative of cosine is minus sine, but the chain rule means you have to take the omega out, and then you get another omega when you do the second derivative. So here, when our dragonflies hover, they tend to bob up and down with a motion that's a very good approximation to simple harmonic motion. Assume that a dragonfly is at x equals a at time t equals 0. So that's basically saying assume that phase term is 0. And that its bobbing motion has an amplitude of 0.4 centimeters and a period of 0.24 seconds. So find the position, velocity, and acceleration of the dragonfly at time t equals 0.1 seconds. So just a reminder of the things we know. Our amplitude is 0.4 centimeters. Our period is 0.24 seconds. We're interested in what is happening at time 0.1 seconds. And we want position, velocity, and acceleration. So I'll give you a few minutes to work this out. So again, we can use this for x, then v of t will be minus a. I'm going to rewrite these over here. So x of t is amplitude times the cosine of omega t, v of t, the minus amplitude times omega times the sine of omega t, and acceleration times time is minus amplitude times omega squared times the cosine. So omega is going to be 2 pi over the period. That's 2 pi over 0.24 seconds, or 26.2 radians per second, 26.2 radians per second. Sometimes helps to think of them as radians per second just because it keeps you in the right mindset. Omega t is 26.18 radians per second times 0.1 seconds, or 2.62 radians. Just again for plugging into things. X is going to be a times cosine omega t. So 0.4 centimeters times the cosine of 6.62 radians. That is negative 0.35 centimeters. Velocity is minus a omega sine omega t. So minus 0.4 centimeters times 26.2 radians per second. The radians go away. Everything is just in seconds. times sine of 2.62 radians. That is minus 5.2 centimeters per second. Which is and then acceleration is minus a omega squared times cosine omega t, which is 0.4 centimeters times 26.2 radians per second quantity squared times cosine of 2.62 radians, which is 240 centimeters per second squared, or 2.4 meters per second squared. And I forgot to put in the velocity in meters per second, but that's minus 0.052 meters per second. In fact, let me add that real quick. So just quickly type that. So that is position, velocity, and acceleration. So let's talk about the period of a mass on a spring. Well, since the force of a mass on a spring is proportional to the displacement and also to the acceleration, mass times acceleration will equal minus kx. So mass times minus a omega squared cosine omega t equals minus k times a cosine omega t. If we divide both sides by a cosine omega t, we get mass times minus omega squared equals minus k. So omega squared equals k over m. Omega for a mass on a spring because acceleration, mass times acceleration is minus kx. Acceleration equals minus k over m times x. And you get omega equals square root of k over m. So that's for a mass on a spring. So increase the spring constant, it's going to oscillate faster. Increase the mass, it will oscillate slower. And you can do similar things for other sorts of harmonic oscillators. So there's a similar relationship for like pendulum, for example. Different values, or like, other values. So the period is 2 pi mass over k, because it's 2 pi divided by omega. We increase the force constant, it'll go oscillate faster. We increase the force constant and mass, it'll stay the same. We increase the mass, it'll oscillate slower. And if we increase the amplitude, it'll stay at the same frequency, but it'll be a bigger motion. So if I have a 0.12 kilogram air track cart attached to a horizontal spring that oscillates with an amplitude of 0.075 meters and a maximum speed of 0.524 meters per second, find the force constant and the period of motion. So the maximum speed is just going to be the amplitude times omega, because that's the biggest value you're going to get from this function. So What do we know here? We know mass, it's 0.12 kilograms. We know the amplitude, it's 0.075 meters. We know the maximum speed, it's 0.524 meters per second. And we want to find the force constant and the period of motion. We want to find K and period T. So V maximum equals amplitude times omega. So omega is going to be V max divided by amplitude, so 0.524 meters per second divided by 0.075 meters, which is 6.99 radians per second. Omega is square root of K over M. So omega squared is K over M. So K is omega squared times mass. So 0.699 radians per second squared times 1.2 kilograms gives us 5.86 newtons per meter. Omega is also equal to 2 pi over the period. So the period is equal to 2 pi over omega. So 2 pi divided by 0.699 radians per second gives us 0.899 seconds. Any questions? In addition, energy is conserved in harmonic motion, just converting back and forth between potential and kinetic. So in an ideal system with no non-conservative forces, the total mechanical energy is conserved. So for a mass on a spring, kinetic energy is 1/2 mv squared, potential energy is 1/2 kx squared, and that will end up equaling a constant. And if you want, you can plug these in as positions of functions of time. So we can find the maximum kinetic and potential energy. The maximum potential energy is 1/2 Ka squared. The maximum kinetic energy is 1/2 mass times amplitude squared times omega squared, which is 1/2 mass times amplitude squared times K over M. which is 1/2 Ka squared, the same value. And if we plug them in as a function of time, 1/2 Ka squared times cosine omega t plus 1/2 Ka squared times sine squared omega t give you 1/2 Ka squared cosine squared plus sine squared, which is 1/2 Ka squared. The total energy is constant. As the kinetic energy increases, the potential energy decreases, and vice versa. So it will look something like this. Energy, potential plus kinetic is constant at all times. This is, cosine squared. This is sine squared. So if you have a 0.98 kilogram block that slides on a frictionless horizontal surface with a speed of 1.32 meters per second, this block encounters an unstretched spring with a force constant of 245 newtons per meter, as shown in this sketch. How far will the spring be compressed before the block comes to rest? And for what amount of time is the block in contact with the spring before it comes to rest? You can think this is, when this hits the spring, it becomes a harmonic oscillator. So I'll let you think about this for a bit. So let's start with what we know. The mass of the block is 0.98 kilograms. The maximum velocity of this oscillation is 1.32 meters per second. K is 294 newtons per meter. We want to find the amplitude, how far the spring is compressed before the block comes to rest. And we want to find the time it takes to complete, what would be a quarter cycle. Go from the middle to a peak. So 1/2 mass and velocity max squared equals 1/2 K times amplitude squared. The mass times Vmax squared equals K times amplitude squared. Amplitude squared equals mass times Vmax squared over K. Amplitude equals mass times Vmax squared over K, all square rooted. So that's the square root of 0.98 kilograms times 1.32 meters per second quantity squared times 245 newtons per meter, or 0.0835 meter. Another way you can do this, Vmax equals omega times amplitude. The amplitude is Vmax over omega. Omega is square root of K over M, so Vmax times square root of M over K. So 1.32 meters per second times the square root of 0.98 kilograms over 245 newtons per meter gives you the same 0.0835 meters. Any questions about that? That's just two slightly different ways of doing the same calculation. So, we want to figure out how much time the block is in contact with the spring before it comes to rest. Well, the time is a quarter of a period. The block goes through a quarter of a complete cycle. It goes from from zero amplitude to maximum amplitude the first time. So, period is equal to 2 pi times square root of m over k, because it's 2 pi over omega. So 2 pi times square root of 0.98 kilograms over 245 newtons per meter. Period is 0.397 seconds. That's the time it takes for one complete cycle. But we're interested in a quarter cycle. Time is period over 4. So it's 0.397 seconds divided by 4. So it's 0.0993 seconds. That is one complete cycle. So let's see. I'll just quickly go over the basics of the pendulum, and we'll go over this again when we get back. So a simple pendulum consists of a mass of negligible size, suspended from a string or rod of length L that has negligible mass, like so. And the angle it makes with the vertical varies with time as a sine or cosine. Though, to be fair, that's only true for small angles. It gets less accurate for larger angles. But for small angles, you can approximate it as a harmonic oscillator. If you look at the forces on a pendulum bob, we see the restoring force is proportional to sine theta, whereas the restoring force for a spring is proportional to the displacement, which is theta in this case. But for small angles, sine theta is approximately equal to theta. For small angles, sine theta and theta are approximately equal. So if we substitute theta for sine theta, this allows us to treat the pendulum in a mathematically identical way to the mass on a spring. And therefore, we find the period of the pendulum depends only on the length of the string. So the period ends up being effectively 2 pi mass over k, where the effective k is mg over L. The mass cancels, and we get period is equal to 2 pi L over G. This is it worked out using torques. The torque is moment of inertia times the angular acceleration, which is the perpendicular force over the radius. We get mg mass times length squared times alpha equals minus mg sine theta L. So alpha equals minus g sine theta. So for small theta, L alpha equals minus g theta. And so theta ends up equaling has a period of square 2 pi times square root of L over G. Now, a physical pendulum is a solid mass that will oscillate around its center of mass, but cannot be modeled as a point mass suspended by a massless string. Here are some examples. A disc hanging from a point, a wide rod that has mass all the way through, a bone. For a physical pendulum, it can be shown the period depends on the moment of inertia. Period is equal to length over square root of length over g times moment of inertia over square root of moment of inertia over mass times length squared. And if you substitute the moment of inertia of a point mass at distance L from the axis of rotation, this gives us expected 2 pi L over G. And so for a clock, the pendulum is designed to have a period of some fixed time. Like a pendulum in a grandfather clock is designed to take 1 second to swing in each direction. So the period is 2 seconds. And so you can find the length of a pendulum that has a period of 2 seconds. But I'm going to stop there for today so we can get started on the lab. So I'm going to stop sharing. I'm going to end.